Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. And I am delighted to have Alex Brown with us today. Hello, Alex.
Hello, I'm super excited to talk about my paper with you
Yeah,
guys.
it's a really nice one, and we'll get to that real soon. Alex, what is your geolocation?
I'm currently in Stockholm in Sweden, so
Ah, so the land of the midnight sun. So
not quite. It's
not quite.
like 11 p.m., so not quite.
Yeah, okay. Very good. Brings the mosquitoes out too.
Yeah, and the humidity.
Yes, and the humidity, absolutely. Very nice. Very cool. And Alex, what do you like to do for research?
So I have like three overarching research areas, which are gravitational waves, and then neutron stars, and then the sort of tests of GR and physics beyond GR. And these kind of overlap in different ways. Like you can
Hmm.
do tests of GR with gravitational waves, you can study neutron stars with gravitational waves, but you can also do neutron stars with E&M. So there's a lot of like things going off of that.
Hmm.
And you can do data and theory and emulation and modeling. So there's a whole
Yeah, there's a whole ecosystem within those three topics.
exactly,
Very
exactly.
cool. And I'm glad you're a triple threat here of observations, theory, and suggestions for experiments. Very
Yes.
cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Can neutron star tidal effects obscure deviations from general relativity? And Alex, take us away.
Yes. So, I mean, I think we kind of just put the entire point of the paper right in the title there.
It's brilliant. It's a great
Yeah.
title. It tells you exactly what the article is about.
So, of course, I should thank my co-authors before I start rambling about my research.
Hmm.
Uh, Badri Krishnan was my PhD supervisor, very helpful on especially the gravitational wave side. And then Rahul and Ingo are great at nuclear theory. They brought in the nuclear theory expertise
Right.
to sort of round out our whole project here.
Very nice.
It's very important.
Very
But
cool.
I
Okay.
think Yeah, so I think part of the reason I really like this project is it brings in all of these things. You have the neutron stars and the tests of GR and the gravitational waves.
Uh-huh.
And if you look in the abstract, there's some different sections in there about like the large uncertainty in the nuclear equation of state, which is
Hmm.
the equation of state describes the thermodynamic properties of nuclear matter, including inside of neutron stars.
Yep.
And when we put a neutron star in a system that's emitting gravitational waves, this matter that's going on affects the gravitational waves. So a black hole is basically a point particle, but a neutron star has nuclear physics going on.
Right.
And so you have to think about the nuclear physics in addition to the gravitational waves. And this paper is sort of exploring how these two things are bouncing off of each other and
Ah,
how that affects the non-GR tests that you want to do with gravitational waves.
right. Because the whole point here is to test it in a strong field.
Yeah, so gravitational waves are extremely compact objects, so they have very high curvature and they're moving really, really fast. So this is one of the best places to test GR because it's some of the most extreme environments in the universe. And so this is where we're really hoping there's new physics, but you have to get a lot of things under control to actually do that. So if we look at the introduction, back up a bit because I have a tendency to just jump in and go straight for the details and get lost and lose the picture a little bit. But basically, we have gravitational waves from black holes and neutron stars. We got the first binary neutron star in 2017, and it
Hmm.
was a really amazing event. It was the loudest event until like last year or so. And it's super close, super loud, which means we can do a lot of cool science with it. And it was also observed in electromagnetic radiation, which allowed us to do really cool things like constraining the speed of propagation of the gravitational wave, which is a
Exactly.
test of GR.
Exactly.
And so we got that and we thought, oh God, there's going to be so many because it's so close. No. Unfortunately, we've only had one more. So we have two binary neutron stars, and then we have a handful of neutron star black holes.
Yes. And I suspect there will be more as time goes on.
Yes, the new release is coming out starting
Yes.
in the next year, and that should more than double our catalog. So we have
Yep.
about 100 total objects, and I think we're looking at around 300 total objects at the end of the
Nice.
data release.
Nice.
So that is an exciting time to be doing this because hopefully we will get at least two more, maybe four more
Hmm.
BNS.
Hmm.
Um, and so this is an exciting time to be pushing these sorts of lines of research forward, in my opinion.
Absolutely.
And as I said, when you're looking at neutron stars, gravitational waves, one of the big things you want to do is study the matter inside of them
Hmm.
because it gives you information on what's called, as I said, the nuclear equation of state.
Yes.
And this is something that at low densities can be studied in a laboratory here on Earth, and
Hmm.
at really extreme densities is controlled by perturbative quantum chromodynamics. But
Yes.
there's this like huge gap in the middle where we can't do anything in the lab and we can't do anything with theory, and we can only study neutron stars. And for a
Right.
long time, this was mainly done with electromagnetism and pulsars. But now we have gravitational waves, and this allows us to study them in an independent way and a really um, more precise way sometimes. So that is one of the main goals often when studying neutron stars is to constrain the nuclear equation of state.
Correct.
And then on the other side, you have testing GR, which is a main goal across gravitational waves, not just with neutron stars.
Uh-huh.
Um, and there's different types of tests, and I kind of mentally break them into theory specific tests and theory agnostic tests.
Okay.
And agnostic tests, you don't need a specific non-GR theory. You can look for effects like the speed of the gravitational wave or Lorentz violation or scalar modes, which you don't expect. These are the sort of things you can do without assuming um, a specific theory. And these are generally done with the black holes for two reasons. One, there's a lot of them comparatively. And two is that they're easier. They don't have all this matter going on.
Oh,
Um, yeah. And so they are a bit simpler to do tests with, which is always nice when you're trying to do a robust test to have less things to take into account.
ah,
But they are sort of limited in a way because matter affects how GR behaves, right? Like, so
right.
having matter effects could lead to violations of GR that aren't captured in a binary black hole measurement.
Okay.
So we still have this data we should use,
Cool. Very.
basically.
Yep.
Uh, Yeah, and so the other type of tests are theory-specific tests, where you use an alternative theory that is formulated. And there are a decent number of these that are reasonably well formulated, but
Yes.
none of them is sort of so good that they stand out way beyond all the rest, and none of them is proven to be more successful than GR.
Right.
So there's, and also in terms of analysis, the waveforms and stuff are way behind GR. So we're sort of just pushing in this direction now. These are just becoming available, the waveforms to do proper analysis with
Cool.
gravitational waves.
Here, we're doing something a little more modest.
Yeah, exactly. We're not basically the point is if you're testing GR and you want to say, I have found a violation of GR, you have to have everything under control. You have to have your noise under control. You have to have your, analysis systematics under control. You have to have the tidal effects under control. You have to have the
Correct.
nuclear physics under control. Like you have to have so many things if you're going to claim that you found a violation of GR. And
Because
so
such a claim would absolutely get attention.
yeah, that's a if you prove that, that's a Nobel Prize winning type of thing right there.
And you don't
After
want
a hundred years of
to. Oh,
Einstein.
yeah.
Yep. But so the goal here isn't to actually find a violation of GR. The goal here is to look at how tidal effects from neutron stars are important in testing GR. So that
Yes.
when we do these tests, we understand if we assume GR is correct in our tidal effects,
Okay.
how is that biasing our analysis? Is this a significant effect? And then the sort of inversion of this is if we're studying the nuclear equation of state and there is non-GR physics, are we going to get our nuclear physics wrong? Which is a
Right.
problem when that's your main goal of your paper, right?
Right.
So that's sort of the goal here is to explore how these two things can bias the other
Yeah.
and look into how we can better look into that in the future,
Awesome.
essentially.
Very cool. I'm with you. Hmm.
Yeah. That's the main overarching goal. And so the paper starts by talking about neutron star tidal love numbers.
Hmm.
And love numbers are, or tidal deformability or tidal polarizability, depending on who you're talking to, are different ways
True.
to, yeah, these are different ways to characterize the matter in the neutron star. And basically, it's just asking how squishy is the neutron star. Like it has a fancy formalism, and it is the ratio of if you put an external tidal field, the object is going to become non-spherical and it's going to be a little perturbed. And the ratio between the perturbation and the field is the tidal deformability.
Yes.
So the math gets complicated, but the concept is pretty straightforward.
Uh-huh.
And There are actually multiple types of deformability because it's an oscillation. So you can have sort of even parity oscillations or odd parity oscillations.
Yes.
And in GR, those are both tensors. In scalar tensor theory, they are not both tensors. There's both tensors plus a scalar.
Okay.
But in gravitational waves, we care about what's called the electric love number, which is the even parity perturbations.
Yes.
And the reason we care about this more is basically that it is the highest order in the gravitational wave. So it's the easiest to measure. The other effects are smaller. And so currently we can't measure them yet. So we're
Mm,
focusing only on this even parity highest order
cool.
love number. And it enters the gravitational wave in terms of a combined parameter that is sort of a mass-weighted combination of both objects.
Yes.
So the gravitational wave actually just depends on both tidal deformabilities combined into one parameter.
I'm with you.
And
Hmm.
that's basically the tidal deformability is the one thing that you can measure, and the other thing you can measure is, of course, is the mass of the object. And if you have the mass and the tidal deformability, you can backwards to the equation of state,
Yes.
basically by looking at the structure of the neutron star.
I'm
And
with
that's basically what this is laying out is how the tidal effects, which is how you get nuclear physics, enters into the gravitational wave there.
you. Hmm.
And also, yes, you've highlighted a very important sentence there, which is
Yes.
that the uncertainty measurements on this are very large right now.
Hmm.
I think I mean, there's a lot of debate on what the constraints are on the tidal deformability, but it's like less than 1,000, maybe you could say less than 500, depending on who you're talking to.
Sure.
And the radius is now within like say 2 kilometers at like a 1 sigma, 2 sigma level,
Yes.
which sounds pretty impressive. Like this object is in another galaxy, and we know the size to 2 kilometers, but
Yes.
that's not very
Impressive.
helpful on the nuclear physics side, unfortunately.
Right.
Not quite enough there, unfortunately. Right. So then I think it talks next about oh yeah. So how you get the tidal deformability. I forgot about that bit. So
Okay.
basically the connection between the EOS and the mass, the radius, and the tidal deformability, which are our observables, is the TOV equations, which are the
Hmm.
structure equations in GR, which is
Hmm.
important. And then you combine that with a second order differential equation for the perturbation of the neutron star, and
Yes.
you get out a relationship between your mass, your radius, and your tidal deformability that is unique to your equation of state.
Okay.
And
Yes. Yes.
yeah, there are sort of two important things that I said there, and one is one is that second order equation, and one is the TOV equations,
Yes.
because the TOV equations are GR specific. So if you go to say scalar tensor theory, which is what we use as a test here, those
Okay.
equations are not the same anymore. And so when you solve them with the same equation of state, you get out a different mass and radius.
Yes.
And if you solve it along with your modified tidal deformability, you get a different tidal deformability.
Okay.
And this is true for essentially all non-GR theories that you have is you have a different structure equation and you have a slightly different tidal equation. And so your neutron star is going to look different when you observe it for a single EOS. And so you're modifying the connection between nuclear physics and astrophysical observable.
Cool.
Yeah.
Very
And
cool.
section 3 here lays out the neutron
Okay.
stars and scalar tensor theory. And this
Mhm.
is actually sort of a whirlwind condensation of an entire paper that I've actually
Book.
discussed before. And yeah, so basically you can derive the tidal deformability in non-GR theories, and this has started to be done in scalar tensor theory, in F of R theory, in Einstein scalar Gauss-Bonnet.
For example.
As you can see, yeah, I'm sure there's some other ones by now, but these have started to come out in the last 5 years.
Yes.
We're really pushing pushing forward on that end. And this is using scalar tensor theory, which is a really straightforward, perhaps the most straightforward alternative that we have to GR,
Right.
because in this case,
So
you're just adding one scalar field. So it's a pretty good test to use because it makes things a lot easier than a more complex theory, even if it's sort of not the most, it's not maybe the most
uh,
physically motivated. It's still physically allowable. It's
fair enough.
not,
It's
in
also
the
the simplest
garbage.
one you can do. So let's do that one
Yeah,
first.
basically, it's a test. It's a
Right.
sort of bed. And, and one thing that is interesting specifically about what we're using here, and this lays out the action, which is so if you compare this action equation here to the GR equation, you can see where the differences are coming in. And so you
Uh-huh.
have your Ricci scalar at the beginning, which is your GR, should be very familiar. And then
Mm-hmm.
everything else after that is the modifications from the
From the
scalar field.
scalar field, phi, 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 lambda phi.
Yep.
There we go. Okay.
Yeah.
I'm with you.
That's just how, you start with that and then you get your field equations and then you perturb your field equations and it sort of propagates down, right, to what you
Cool.
actually want to observe. And
Mm-hmm.
there's some, I referenced some papers. There's an earlier paper from me from 2023 and one from Gaston. And so there's some papers that actually lay out all of the mathematics if somebody else is interested in that. But
Very
I
cool.
think the key thing here is talking about the specific theory and why it's a bit interesting. And I think the definition is on the beginning of the next page.
Yes. Okay. So
But
we're gonna
we're using what's called,
integrate that up. Okay, I'm with you. Mm-hmm.
so this is DEF or De Moivre-Esposito Frese or spontaneous scalarization case. And this is the one that's often used because scalar tensor theory is very tightly constrained in a certain regime in the solar system. And the interesting thing about this specific theory is because of the functional form of the scalar field tied to the metric is you can get extreme changes in strong field without having noticeable effects in the weak field. So it can pass everything that we have in the solar system and still do really weird things inside of neutron stars.
Yes. So
And that is
satisfies the
what's
weak
really
field.
interesting.
Yep. Yep. Mm-hmm.
Yeah, so that's spontaneous scalarization. And also the thing that's interesting about the scalarization is that it's a sort of non-perturbative effect. So you can't capture it just by adding like little terms to your waveform, which is something that you do in a lot of tests of GR. You
Yes.
just sort
Okay.
of add a little delta and see if it comes in. We can't do that here because it appears under certain conditions in weird spots, and
Okay.
it's not here in those tests.
Cool.
So basically, this here just discusses the regime that we're looking at, and we're looking at sort of the most extreme reasonable regime. So it's like the 2 sigma upper bound on how far from GR you can get.
Okay.
And the reason we did that is because anything closer to GR is going to have just a lesser version of the effects that we talk about here.
Yes. Yes.
So if
Yes.
you can't distinguish this extreme theory from GR, you're definitely not going to be able to distinguish something that's closer to GR.
Okay.
It's not going to work.
Uh-huh. Uh-huh.
And
Yes.
so this just sort of lays out the experimental constraints and
This is the
that decision that we made.
with you. Mm-hmm.
So
Cool.
then the next bit is the nuclear equation of state, and this is where my colleagues were super helpful coming in. And we use a meta model for the equation of state because as I said, there's a lot of uncertainty in the equation of state, but we don't want to like throw out anything we have from nuclear physics. And so what we do is we have a equation of state that is broken into 2 parts. So you have like a low density equation of state, which is
Got it.
below 2 times the nuclear saturation density.
Okay.
So the density of, like an atom of a nucleus in an atom is low density here.
Yes.
Below that, you have, yeah, exactly. You have a model in terms of nuclear empirical parameters.
Mm-hmm.
And these can be constrained in a laboratory on Earth using different,
Experiments.
using different experiments. So
Let's see.
this is how we bring in our sort of nuclear physics. And
Okay.
what my colleagues have done is sort of expand around the symmetry energy, which is related. Oh, sorry, first the energy per particle of symmetric matter, which
Yep.
is basically telling you about matter when you have equal number of protons and neutrons.
Yes.
We know a lot about that because that's what we have here on Earth. That's the one
Uh-huh.
we know
Yes.
more about. So we can expand around that in like similar to the Taylor series or any sort of series expansion and
Mm-hmm.
capture higher order terms with different coefficients. And that's what's shown in the,
Uh-huh.
yes. Each
Yep.
one of those is a coefficient that you can constrain via some laboratory experiments or via an analysis like this. And then you have the second expansion, which is designed to capture what's going on when you have neutron-rich matter. So
Yes.
matter here on Earth is pretty much proton, neutron roughly equal, but a neutron star has very few protons.
Yep.
And so we have to capture that behavior. And this is where a lot of the uncertainties are because we can't study this as easily in a laboratory.
Right.
So if you look, we have all these coefficients and the highest order coefficients. So the Q and the Z, which I think are the 3 and the 4, those
Mm-hmm.
are set to 0
Okay.
because
Okay.
they're either so small or like negligible that we don't have to worry about them here.
Okay.
And then We have the ESAT, which is the top E, which is related
Uh-huh.
to the proton and neutron energy. That one's we know very well because of laboratory experiments, so that one is fixed. And then we have the four other, um, yeah, so we have the four other terms, which are the that one and then the first three of the next equation.
Correct.
For
Yes.
all of those, we have a uniform prior that is informed by nuclear physics.
Nice.
So that is how we sort of randomly sample from those to construct a low density equation of state. And then we need to sort of move into the neutron star, which is in a regime where this equation of state falls, we don't expect it to be reasonable anymore.
There you go. Hmm.
And so we have to expand this somehow. And there are lots of different ways to do this, but we use a speed of sound parameterization.
Yes.
So basically, yeah, it's pretty commonly used in neutron star studies. So basically, from 3 times, 4 times in intervals, up to 8 times nuclear saturation, you randomly draw a number between 0 and the speed of light squared. And
Hmm.
this is your speed of sound, and then which is the derivative of the pressure and density.
Yes.
And you use this to sort of manipulate your curve. So if the speed of sound says it has a sharp bend, then you have a sharp bend. And so it can be smooth or it can be sharp bend, which is simulates a phase transition. All of those are kind of captured through this broad family. Um, and that's sort of the goal here is to sample a wide parameter space while
Mhm.
keeping in the nuclear physics we have at low densities.
Very nice. I'm with you.
And so,
Okay.
yeah, so that is basically our EOS. It has 10 parameters, and there are 2,500 equations of state that we use in our analysis. So it's a relatively broad sample, but it's not,
Okay.
completely comprehensive. We just we sample 2,500. We don't construct it on the fly, just due to computation time,
Oh,
basically.
yeah, yeah, yeah. Sure. These are pre-computed. Uh-huh.
Yeah, they're pre-computed. Otherwise, it takes a long time, especially with the scalar tensor stuff going on. So the data analysis portion that we do here is using gravitational wave data analysis.
Uh-huh.
And the sort of method here is pretty standard sort of Bayesian inference for gravitational waves. But I realized recently in giving a talk that a lot of us don't define how this actually works. We just hand wave it a bit.
Basic.
Um, yeah, so it's based on Bayes theorem, which is, everything in this field. But Bayes theorem and Bayesian inference, I think, are actually surprisingly powerful and really interesting tools where you basically have this theory that says that your posterior distribution, which tells you how likely a parameter is, say the mass is,
Yes.
given your hypothesis, which for us is a gravitational waveform, and your data, which for us is time series data from the gravitational wave detector. And
Yes.
so you can calculate how likely a parameter is given that using just the likelihood and times the
Prior.
prior over the evidence. And the likelihood is sort of that's a bit tricky because it is the likelihood of the data given the parameters.
Yes.
And this is the thing that you have to calculate a lot of times is you draw random parameters and then you calculate the likelihood and you're trying to find the highest likelihood essentially, but you have to
Yes.
calculate this every time.
Yes.
And this is why we don't have EOSs generated on the fly because then you'd have to calculate that and the likelihood and that would just make it
And that takes
slow.
a little bit of time. Yep.
Yeah. So then you also have the prior, which is they can be really important, but we generally go for broad but physically reasonable. So I mean, there's some things
Okay.
like the object has to be on the sky. Like this is pretty straightforward.
Order.
But yeah, the object is on the sky. But actually, in this case, we know where it is because it had the electromagnetic companion. So
Yep.
we can fix the sky location. We can fix the distance. And then the other things like the inclination of the system are just a uniform prior
Hmm.
across the parameter space. And in terms of the masses, we have a uniform in chirp mass and in mass ratio, which is sort of uniform in combinations of the masses as opposed to uniform in individual
In
masses.
individuals. Yes. Okay.
And
Hmm.
this is easier to constrain because of the way that the masses appear in the gravitational wave, essentially.
Cool.
So it speeds up your inference a little bit. And then, of course, you have the tidal deformabilities. And in this case, one thing that is a bit different here is how we sample the tidal deformabilities, because there's a lot of methods in the literature for how you get the tidal deformability and how you constrain that in your analysis.
Okay.
So we use a method that was published, I think, originally in 2020 if I'm remembering my history right. And basically, what we do is the sampler draws an equation of state. So it's just like a number out of those 2,500.
Yes.
And then you can calculate the tidal deformability of one of the objects from the mass.
Okay.
And then you can calculate the tidal deformability of the other object from the mass in sort of a lookup table. And
Nice.
this has a really useful property that we are making both neutron stars have the same equation of state, which
Correct.
is what you expect. Like,
Wow.
like nuclear physics should be nuclear physics.
Yeah, there's only
Every
one real one.
yeah. Otherwise, Astro just doesn't work.
Hmm.
So we
Hmm.
have to assume nuclear physics is nuclear physics, and there are different ways to do this. But like early analysis would just sample randomly the tidal deformabilities, and you're not seeing any physical connection. So that's why we sample the equation of state and then calculate the tidal deformabilities from that.
I'm
So I
with you.
think that's the only main sort of interesting trick that we do there. And we mentioned here that we use a package called
Nice.
Dynasty, which is a nested sampler. And this is really useful because it allows you to calculate the evidence, which is like the last little piece of Bayes' theorem, which is how likely your data is given your hypothesis. So
Yes.
given your waveform, how likely is your data? And this is really useful because you can compare hypotheses. It's independent of your parameter set.
Yes.
So it doesn't matter if your mass is this or your lambda is this, none of that matters. It's across all of them. So if you
Correct.
have two different hypotheses, you can compare those and it'll give you an idea of whether your data supports one hypothesis over the other.
I'm
And
with you.
in this case, we look at obviously scalar tensor theory versus GR
Hmm. Hmm.
case.
Cool.
Um, so that's why we use Dynasty.
Very cool.
Um, I think, yeah.
Okay. Yes.
Yeah, and that's just the last equation there. And there's a little more details on the gravitational wave side, like the waveform that we use, which was when we were doing it the most up to date, but these things just change like constantly.
Yes. Yes.
The,
It's a
the
live
wave,
active catalog. Hmm.
yeah, exactly. The waveform community is constantly making improvements. Um, yeah, so that is the gravitational wave part. And then there's the little bit here in the next paragraph that is about the E&M constraints. And so what we want to do is take our gravitational wave constraints and compare them to our electromagnetic constraints to sort of look at, again, this large uncertainty that we have in the nuclear equation of state. So the uncertainty coming from the nuclear physics side is captured in like the width of our equation of state, like catalog that we use.
Yes.
That's sort of capturing the uncertainty coming up from the nuclear equation of state.
Uh-huh.
But by incorporating these constraints from pulsars, we can bring in what are the constraints from the astrophysical side in this
Cool.
regime. And so we use two
Uh-huh.
nicer pulsars.
Uh-huh.
Um, and we pick these two pulsars because they each have two analyses done by NICER. So
Yes.
they're a bit more robust. You have two papers on them. And so we use both of those papers and we just require that an equation of state is consistent with at least one
One
paper
of them.
and a
Hmm.
one signal level. And then the other constraint that we have is the high mass.
Yep.
So the maximum mass of that the equation of state can support is actually a really important parameter
Yes.
in the equation of state. And so when we get more massive pulsars, it sort of cuts off certain equations of state. And
Uh-huh.
so what we did here is we require the mass of 2.18 solar masses, which is, I believe, the one sigma lower bound on our most massive pulsar.
Okay.
So we know that an equation of state has to be able to support a neutron star of this mass. So we
Yes.
do like a hard cutoff. Anything below that gets sort of out of the
Oh.
analysis.
I'm with you.
Yeah, and I think that basically that brings us to the results in the discussion. If you want to go up to the figure, and I
Yeah,
can just
let's
sort of walk through
go
it.
year one here. Okay. Pull this
This
up a
figure.
little bit. Neutron star mass radius. Okay.
Yeah, so I think the first thing to clarify is that um, on the left is left and right's a struggle is GR, and
Uh-huh.
then on the right you have scalar tensor theory.
Yes.
And so those are the two different panels that you have, and then you can see they're basically
Ah.
the same structure of plot. And so we'll walk through what's going on. And this is a posterior, so it's showing the prediction on the parameters. And
Uh-huh.
so in the middle we have the mass and the radius. And the equations of state are represented in the back there by those curves. So
Yes.
all those curves are our 2,500 equations of state represented as mass radius relationships.
Cool.
And the color here corresponds to the support from the data and the cutoffs, the sort of astrophysical cutoffs. And so if it's very light, there's no support. And if it's lighter, then there's some support. And then darker is the most support from the data.
Gotcha.
And so I think the first thing you can see is just looking at these two really fast is that the mass radius relationships are completely different
Yep.
in these two
Right.
theories. This one
Yep.
has a very strong bend and it has a lot higher
Right.
mass on average.
Yes.
And so this is the exact effect that we're looking at here. And then into the center,
Mhm.
the colors in the middle that these show the SNR, so the signal to noise ratio, showing you where the mass of the object is. So since these curves cover a lot of space, you can see the actual mass of the first object and the mass of the second object are those circles in the middle there.
Uh-huh.
Uh,
Okay. Yes.
and yes, you can see that for the GR case, the masses are kind of really nicely agreeing with that one nicer pulsar in this analysis, which is always
Oh,
good. Here,
good.
the NM constraint. And if we look at the top of the plot, so above the middle, you have the 1D posterior on the radius.
I'm with
And
you.
so this shows you your two radii. And then on the side of the plot, you have your 1D on the masses.
Mm-hmm.
Um, and you can see we have the slightly angled prior because the prior was on, the priors are shown in the lighter lines.
Right.
Um,
Right.
yeah.
And what are
So,
you got a bunch of vertical lines here on
yeah,
the
so the vertical
here?
lines are
Oh,
like they
in
show
this
you
case.
the boundaries of so those are the 95th percentile credible intervals.
Okay.
So and those are the numbers quoted also on the plot. So these give you an idea of sort of where the boundaries are on the analysis. Yeah, so you can see whether they line up. Like if you look at the radius of the GR case, they're very similar, right? Like all the
Yeah.
lines are very close.
Yep.
Uh, so
Less.
that's basically everything that's going on in those, except
Uh-huh.
for, oh, I forgot the constraints. So we show our mass constraint by this horizontal line. That's our pulsar constraint, this like dashed yellow
Upper
line.
bound. Yes.
So everything less massive than that is goes away, which you can see there's this like bunch of equations of state in the GR case that have been excluded by this cutoff. And
Good.
then we have these circles or ovals, I guess, representing the nicer constraints.
Yes.
Um, and you have the two colors, basically the two groups that did the analysis. So you have the Riley et al. And the Miller et al.
Mm.
I think one thing that is
Right.
interesting is if you look at the GR case, it lines up a lot nicer with the Riley analyses. And then if you look at the scalar tensor case, it aligns a lot nicer with the Miller et al. Analyses.
Interesting.
I
Okay.
think this is a really interesting thing that
Yeah.
shows how these E&M constraints and these astrophysical constraints from other sources can really help us in the GR community look at what's going on here.
Right.
Because right now, both of these are consistent with the large uncertainty.
Mm-hmm. Mm-hmm. I'm with you.
And so if you're looking at right, we're trying to measure the mass and the radius and the equation of state. So if we look at the mass, the 1D on the mass, which is on the sides there, we
Yep.
can see that the mass of the two components is the same in both
Yes.
analyses.
Uh-huh.
And this is not actually super surprising because the mass is a very dominant term in the waveform.
Okay.
And so this is, kind of what it's not unexpected, basically.
Right.
But if we look at the radii, that's where we see something interesting
Mm.
because in the GR case, they are very, very similar.
Yep.
They're both 12.4, 12.3.
Mm-hmm.
If we look at the scalar tensor case, we have one that is at that 12.3, but the other one is at like 13. So it's an entire kilometer larger.
Right.
This is the high mass object
Mhm.
now has a higher radius.
Okay.
And this is sort of the really interesting thing here, right? Is the only thing that's happening here is that the neutron star structure has changed because of GR effects. And now we have different radius measurements.
Okay.
And both of these radius measurements are completely consistent with everything we know. So we know, because we did this analysis, that this is GR and this is scalar tensor theory, right? But both of these could be correct. There's no
Okay.
reason
Yes.
to exclude both of these, right? So this is sort of the answer, right? Is this could be just like tidal effects can be obscuring deviations from GR because it can just be absorbed into this large
Correct.
uncertainty. in the
Correct.
radius.
Correct. Going back to the title of the article. Yes.
Yeah, exactly. Yeah,
Yes.
so you have this large uncertainty in the radius, and both of these are consistent with that. So
Mhm.
we're hiding, sort of obscuring it a bit there. Um,
Okay, so there's a certain degeneracy, but maybe we'll come to that later. Mhm.
Yeah, yeah, basically. And so, I mean, that is sort of the main thing here is that you do get different radii when you use two different theories. And the only thing we've changed here, I want to clarify, is the tidal effects. The waveform actually hasn't changed. When we did this, the
Right.
scalar tensor waveforms were not available. Um, and so this is only looking at the structure of the neutron star, which is the variable we're trying to isolate anyway. So
Yes.
just by changing the structure of the neutron star, you get a significant change in the measure of the radius of a neutron star,
With you.
which means that if you are testing GR, you are, say, you want to do a test of scalar tensor theory, and you don't include these tidal effects, you could be off by an entire kilometer, which is the same as your 1 sigma error bar. So like, that's not good.
Right. Right. Okay.
So this is showing that
Cool.
you really should be taking this into account, these tidal effects, not just the effects on like the waveform or
Right.
the system, but also on the individual objects itself.
Cool. I'm with you. Hmm.
And then if you look at the next, the other figure, there's only two,
Okay.
that
And
one is actually going to bring back the question of the nuclear equation of state. So as
here
I
we go.
said, one of the main
Barriers.
goals, yeah, that one of the main goals is always to study the nuclear equation of state. That's often what we want to do when studying neutron stars. And so what we have here are 1D posteriors on the first four are the nuclear parameters. So the things from the low density equation of state.
Uh-huh.
And then the last panel is from three times is the speed of sound. So this is the first term in the high density
Mhm.
equation of state. So if you look at the first four panels, they are the top and bottom. So the top is GR and the bottom is scalar tensor theory. And you
Okay.
can see that the first four panels are just consistent with each other.
Let's see.
So
Yes, I'm
um,
with you. Uh-huh.
yeah, so
Good.
currently it looks
Not
like
so
the
much here.
changes from scalar tensor theory are not affecting the low density equation of state
Right.
measurements right now.
Okay.
And this is because what we'll look at in this last panel where you see something different, right? So this is
Right.
happening, this is the speed of sound at 3 times nuclear saturation density.
Hmm.
And so you see that in the scalar tensor case on the bottom, we're basically getting the prior back out again. So we're not really getting a lot of information.
Hmm.
That or all of these speeds of sound are equally valid is basically what this is saying.
Okay.
But in GR, we have a very strong preference towards a speed of sound closer to the speed of light here.
Mm-hmm.
And the reason this is happening at 3 times nuclear saturation density is because this is the average density in the center of the more massive neutron star.
Yes.
So if you think about the plot that we saw before, the radius of the more massive object was different
Yes.
because of the equation of state. And that is sort of being reflected here as the speed of sound constraint is related to that radius
That curvature.
constraint.
Okay. Okay. I'm with you. Cool.
Yeah,
Mm-hmm.
it's a bit of a
No, I'm with you. It's good. Uh-huh.
But basically, this is sort of one of the other key takeaway here is that if you're studying the equation of state, which again is one of the main purposes of studying neutron stars, you can be wrong if there's some non-GR physics that you aren't accounting for. You know,
Okay.
you do this test and you don't realize there's scalar tensor effects going on, and now you think that you think that the speed of sound is say like 0.75 plus or minus some error bars, but actually it could be anywhere between 0 and 1.
Yeah.
Um,
Yes.
so this is something you want to consider if you're making strong statements on your equation of state. Have you considered this picture that other physics could be going on?
Correct. Okay.
And this is very important in the broader context, which I think the text here discusses, because there's obviously the equation of state in terms of the nuclear physics side is its own ongoing research, completely separate from the
Absolutely.
astrophysics side.
Hmm.
And
Absolutely.
one of the questions that is being explored is whether this low density meta model equation of state is valid up to 3 times nuclear saturation, which is where we are getting this deviation between GR and non-GR.
Right.
So if we expanded our low model up to 3 times nuclear saturation to see if that is a valid thing, we would get different answers. from having these different theories, which
Yes.
means
Okay.
because we see the differences at 3 times nuclear saturation. And so if you want to study anything around 3 times nuclear saturation and you're missing some physics, you're going to bias your results.
Okay.
Um,
Yes. Very cool. Oh, that's really curious here.
yeah.
So if you crank up the speed of sound of 4 times NSAT,
Yeah, then they're the same again because it's above the density of this specific system. Now, if we got a binary neutron star merger in gravitational waves with more massive neutron stars,
okay,
then we could possibly constrain a higher density.
I'm with you.
So basically, the density constraint is based on the mass of the neutron star,
Mm-hmm.
and these are both on the lower end. But if we had something, up at 1.9, 2.1, then we would get constraints in the higher density regimes.
Yes.
Uh, but we don't have that right now, sadly. So we can't see what would happen.
Soon,
And
I
of course,
promise. Soon, I promise.
hopefully. But yeah, and of course, the nuclear empirical parameters will be constrained more on the nuclear physics side. There's some, lots of experimentation going on there, and that will sort of constrain the lower side. Um, and then the GR and NICER are focusing on this middle regime. Um, but yeah, I think that is basically what we're discussing throughout this is the importance of, for instance, 3 times the speed of sound at 3 times nuclear saturation, um, because this is quite close to the regime of nuclear physics in terms of the full expansion,
Uh-huh.
and there are different reasons to study it. Um, yeah, and I think I've gone over the two big takeaways there, which is that if you want to study GR
Yes.
with neutron stars, you have to take into account the effect of non-GR on the structure of your neutron star. You
Yep.
can't just change your gravitational wave and be like, okay, because you could have a, 1 kilometer off measurement on your neutron star,
Right.
which is the same as like the error boundary. So you're just completely taking yourself out. And conversely, if you are trying to make strong statements about your nuclear equation of state, if you're trying to argue that the meta model is valid up to 3 times nuclear saturation, which is a big discussion,
Yep.
you need to consider, could there be other physics going on in terms of the neutron star, like the gravity that is biasing your nuclear physics inference?
Very cool.
And yeah, that's basically the goal here is to say you have to take these into account. And of course, in the future, more sophisticated analyses, looking at how this is, happening in different theories, so on and so forth. But the goal here is basically to say we can't ignore this. If we're testing GR, you can't assume that you have GR tidal effects, especially not as we get more and better data.
Yeah.
We have our detectors are a lot more sensitive than they were in 2017, which is
Sure.
8 years ago now. They're a lot more sensitive than they were. And 3G detectors in the 2030s are going to have an order of magnitude more SNR. And so
Mm-hmm.
if you neglect this effect, like this, you can't really do that.
You're also missing, you would be missing a strong test of GR in the
Yeah,
strong.
exactly.
Oh, yeah, you got to do
So
it.
you want to use neutron stars. They're really valuable, but you have to carefully consider the nuclear physics and the non-GR physics in a sort of more sophisticated way than just, oh, we'll just sample the tidal deformability, or, we'll just assume GR is okay for the structure of the neutron star. Yeah,
Right.
and I think that's
And
our big takeaway
very
there.
different US. Very cool. Very cool. Alex, beautiful paper.
Thank you.
Thank you so much for walking us through
Thank you.
that
I'm very
awesome
excited to
title.
keep
I
talking
love
about
the
it.
title of this one. It's great. It's very good. Very cool. Let's see. You kind of touched on it a couple of points, particularly there at the end, but let me just push on it a little bit more. Um, where do you think we go from here, given the published article? There will be, of course, more LBK data coming on.
Yeah.
There's next generation stuff. Of course, there's always serendipity. Maybe we get lucky on
Yeah.
one or two. But where do you think we go from here, given the published article? And
Yeah, so there's actually a lot of one thing that is interesting is these pieces of this are being pushed forward from a lot of directions.
Mhm.
So waveforms in scalar tensor theory, so the full gravitational waveform is now available, and I'm collaborating with one of the authors on that so that we can do this test with also the waveform
Yes.
being the non-GR waveform. And so that is a more sophisticated test of the scalar tensor aspect.
Hmm.
This has just isolated the effects of the structure of the neutron star, but that is a more comprehensive picture of the problem
Right.
overall.
Right.
And then there is the nuclear physics side. Of course, there is like a lot of there's laboratory experiments going on. There's
Hmm.
also more sophisticated developments of nuclear, like the expansions. So instead of doing a speed of sound parameterization, you can
Yeah.
do a Gaussian process or some other more complex fitting to the equation of state, including the low density
Hmm.
equation of state. So there's a lot of push forward there, and like also how you bring that into the analysis. And of course, we are about to have a huge data release from the LVK, which will, I think, triple our catalog is the current estimate. And so there's a lot more events coming in, and they will be of a higher sort of SNR on average. And so that is good because the tidal deformability, if we can drive down that uncertainty, that will definitely help with this sort of problem going on. NICER is doing a lot of work, so the pulsar constraints should be getting better. So all the pieces are sort
We're
of
coming
improving,
in.
and we'll just keep pushing.
Very cool. Oh, it's really it's an exciting time to be working on these topics. There's a lot of activity, and that always makes for great science. So very cool. Well, I really look forward to seeing these developments come out, and maybe we'll do a third video. All righty. Thank you again, Alex, for walking us through your very awesome article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.